Hi, I'm Ushma Neal with the Journal of Clinical Investigation. Would like to welcome you to the next in our series of Conversations with Giants in Medicine. Today I'm honored to be joined by Dr. Francis Collins, who needs little introduction. After getting his PhD in physical chemistry at Yale and his medical degree at the University of North Carolina, Collins zeroed in on genetics as his area of concentration and is noted for his landmark discoveries of disease genes, and later his leadership of the International Human Genome Project, which culminated in April 2003 with the completion of a finished sequence of the human genome. Since August 2009, Collins has served as the director of the National Institutes of Health, which is the largest supporter of biomedical research in the world. We welcome the chance to hear more about your very unique trajectory through science. Do you think you could start by telling us a little bit about your path to medical school?
My own path was, let's call it, nonlinear. I never really imagined growing up as a kid on a small farm in the Shenandoah Valley, Virginia, that medical school was something I would want to do. My parents were in the arts and theater and music. And when I got to 10th grade chemistry, I had this revelation that science was actually really exciting. And I hadn't necessarily expected that calling, and there it was. But it was chemistry. And biology, by the way, struck me as a high school student as being much less interesting, probably in part because of the way it was taught. It seemed very descriptive, muddy, I didn't understand there were very many principles there. Chemistry, physics, much cleaner, let's stick to that. So I went off and got my college degree in chemistry and then did a PhD in quantum mechanics at Yale, following up on this desire to have things that were mathematical and based on first principles. I loved second order differential equations. But somewhere along the line, I felt this urge to expand my horizons a little bit, realized I'd gotten kind of narrowed rather early because I went to college when I was 16 and I was already close to finishing a PhD in my early 20s. So I decided to branch out a little bit and see what was going on in other fields and discovered that actually biochemistry, genetics were truly exciting fields that I'd sort of missed. And this was at the point where recombinant DNA was emerging and it looked like this is a field that's about to break wide open. And hey, maybe I better have a look at that. Then I got into a bit of a crisis of where I was going because I'd had this plan all along which was focused on chemistry, and now I was feeling led in another direction. And I had some uncertainties about whether I was even cut out to do research. Maybe that was part of this career-changing moment. And I decided to go to medical school to basically focus on the science of biology, particularly as it applied to humans, but also to sort of keep my options open. Now, why any admissions committee would listen to that story and allow me to come to their medical school, we could debate that, but they did. And off I went to the University of North Carolina in 1973 as a medical student, totally unclear about what I was going to encounter, but excited about the opportunity. And it was in that first year as a medical student that it all began to sort of come together, and particularly at the hands of a professor of pediatrics who for all of 6 lectures taught us about human genetics. And he brought patients to class and he explained how very subtle changes in DNA could result in very significant changes of a medical sort for sickle cell disease, for neurofibromatosis, for Down syndrome. And I was hooked because it brought together my desire to stick to things that were principle-based and almost digital, with a desire to be involved in science that directly related to humans, and this sense that something was happening here in human biology and that genetics might very well be the place where it happened most rapidly. So that's what I decided, that's what I want to do.
Okay, so your interest in genetics really was rooted in medical school, but then you went back to Yale to do a postdoc with Sherman Weissman, was it? And that was where you really started to entrench and looked into chromosome jumping, correct?
That's right. So I went all the way through medical school. I did a full residency in internal medicine. I was a chief resident at North Carolina Memorial Hospital, and then I went to do this fellowship in human genetics at Yale with Sherm as my mentor. And I got to say, those first few months in the lab were very stressful. I had not done this kind of research. I didn't know how to use a pipette, man. I mean, An autoclave? What's that? Remember, my research was in quantum mechanics, and most of it was highly theoretical. So I was like a beginning graduate student, except I was supposed to be an MD, PhD, highly trained postdoctoral fellow. So it was a rapid learning curve with a lot of bumps along the way. But ultimately, I started to get my legs under me. And on a rainy day in New Haven, there are a lot of rainy days in New Haven, Sherman and I were talking about sort of what's the big challenge here that's coming up for human genetics. And it was clearly, how do you go from a general sense about where a disease gene is located on a chromosome? Because the whole idea of using linkage analysis to do that was emerging. Botstein and his colleagues had written that paper in the American Journal of Human Genetics. It made it sound like there was a general strategy for getting to the answer for diseases whose biology we didn't understand, but whose genetics we could describe. And it was clear you were going to need to cross large distances in human DNA. And remember, there was no Genome project, there was no database you could just go and click your mouse on. You had to do this in the lab, and that's where the idea of chromosome jumping emerged, that you would develop a method by having very large fragments of DNA who are diluted to very low concentrations and then ligated into circles. And if you could rescue the junctions of those circles, those were basically jumps that would take you from point A to point B, which could be quite a distance away. And that became a big part of my early efforts as a senior postdoc and then as an assistant professor at Michigan.
Right. And in Michigan was where you really started to find more of the disease genes. That must have been enormously engaging and interesting.
So I got to Michigan, starting out my lab, in a wonderful moment there at Michigan where a lot of other remarkable investigators were arriving in that sort of 2 or 3 year period that Bill Kelly, the chairman of medicine, had arranged by being a very effective recruiter and having supplied kinds of packages that many of us thought were pretty interesting to get started. So people like Jeff Leiden and Craig Thompson and Gary Nabel, Jim Wilson, John Lau, all arrived within that period. Dave Ginsburg, who's still there, he's the only one still there, the rest of us have scattered. What an amazing environment that was.
Right.
Encouraging you to really think creatively. I had joint lab meetings with Dave Ginsburg for several years, which just added to the enormous scientific energy of what was going on. So I wanted to tackle some really significant problems, and based on my own medical experience, cystic fibrosis had always been an appealing target and one that desperately needed answers about what the real cause of this was, what was the gene which, when mutated, would cause this disease. So chromosome jumping seemed like an appropriate way to go after that. And so did Huntington's disease, so we got involved in that. And after a while, so did neurofibromatosis. The most common disease that I saw as an adult geneticist in my Friday clinic was neurofibromatosis type 1, and it seemed like it was time to find that one out too. So probably a little overambitious to take on 3 major disease gene hunts at the same time in a very small lab, but oh well, when you're young and enthusiastic, you think you can do these things. And I was fortunate to have great people who came and joined me in my small lab and to develop collaborations that made things possible that we could not have done ourselves. And that was certainly true for Huntington's disease. That was certainly true for cystic fibrosis.
Right. Now, I've seen you give several talks in the recent past that were more focused on progeria, something that you've focused on more recently. And you've always shown pictures of patients that you've treated. So
yes.
It was at least clear to me as an audience member that you definitely rooted your research in the individual and in your clinical care and your interactions with people. So how has being an MD and especially looking into genetics and specific patients that you've treated influenced the way that you approached your research?
Almost every disease project that I've worked on represents a condition that I met first in the clinic and got intrigued by and wanted to understand better. And that applies to cystic fibrosis, to neurofibromatosis, to Huntington's disease, all things that I saw as a doc trying to understand or give advice to people who were affected or their families before it became a research passion. Same with progeria. I met Meg Casey in 1982 when I was assigned to care for her as a genetics fellow at Yale. She carried the diagnosis of progeria, although actually she had a version of that that was not exactly the classic version. And I was deeply intrigued and puzzled that we didn't know any more than we did about this disease of premature aging. It was only 17 years later, encountering a couple who had a little boy with progeria, that it became possible to think again about this and ultimately to make it a major project in the lab as it is until today, with a major set of insights that have occurred in just the last 8 years about the cause of this and what to do about it.
In 1993, you succeeded James Watson as the head of the National Human Genome Research Institute and embarked on what some might say was the most ambitious biomedical project in history, the decoding of the human genome. Can you talk a little bit about the challenges that you faced, the competition with Craig Venter, and ultimately how joyous it must have been to finish the first draft?
Well, that's quite a saga. It's hard to put into a few minutes, but I'll try to hit a high point or two. Well, first of all, how did I end up in this role? Jim Watson was the first director of the Genome Project and was very effective in both generating scientific enthusiasm, which people may not remember these days, was actually pretty limited. At the beginning of the Genome Project, most of the scientific community was opposed to it, thinking that it would be impossible technically. It would end up being too expensive. It would take money away from other things. But Jim, with his remarkable rock star status, was able to give this the kind of credibility, both in the scientific community and in the Congress, that it needed to get it started. But very quickly, in the space of 2 years, suddenly things went wrong and Jim resigned, and there we were. I had at that point started a genome center, one of the first 6 at the University of Michigan. I was a Hughes investigator. I was happy with my life as a researcher, as a person taking care of patients, teaching medical students. I had the perfect sort of life plan here for the rest of my career, and all of a sudden the phone rings and somebody says, "We want you to apply to be the next director." And I said, "That's crazy. A federal employee? You've got to be kidding. That's the one thing my mother told me never to do, is to work for the government." So I actually sort of ran away from this for a while. But ultimately, the opportunity to stand at the helm of what history, I think, will regard as just about the most significant scientific effort that we've undertaken in the last many centuries. Well, how could you turn that down? So with great anxieties about what it would mean, great concerns that the project might fail, because when I started in April of 1993, we were just barely beginning to get going. Promises had been made that this was going to get done in 15 years. That we were going to somehow scale up the ability to read out DNA bases to the point where you could do 3 billion of them in a measurable period of time. And at that point, you know, if you did 1,000 in a day, you were doing pretty well. So it was hugely challenging to imagine how this would go. But it seemed just too interesting to pass up. And because the project was so interesting, and because Jim had started the process of recruiting some of the best and brightest to come and join, and I had the privilege of continuing that, and people got excited about it and said, "Well, yeah, I don't know what else I could do, but this sounds like what I want to do now." We developed that team, a remarkable group of dedicated individuals, and the energy that went into that, and the creativity as far as technology development, and the ability to work with model organisms, which was a very wise decision of the planners, to be able to understand how you could read large amounts of DNA and begin to understand what that meant. All of that was a solid trajectory. And by 1998, I think we were all beginning to believe that this might actually succeed, although getting it done in that 15-year timetable still seemed like it was going to be a heck of a stretch. There was, at that point, then arriving on the scene, a challenge from a private entity. And that was an interesting juncture, in particular because it brought this project, which had mostly been under the public's radar, out into a much more public space. Not all of that was good, in the sense that there was way too much focus on this being a race for the human genome, and too much focus on differences in technologies. We were all using the same machines. And maybe way too much focus on personalities,
right,
in terms of who had a yacht, that was him, who had a motorcycle, that was me. I mean, who cares, really? Let's just get this science done. But it did sort of, I think, give us a chance to have this groundbreaking historic project reach the consciousness of more people, and that was a good thing. The real difference, which I think a lot of people missed, was not so much the scientific strategy. It was really the approach of how was the data going to be made accessible. One of the proudest moments, I think, for the Genome Project was that decision in 1996 that all of the data would be made available every 24 hours immediately, so that anybody who had a good idea could use it, not waiting for publication, not filing any intellectual property claims. And that was a decision which is now reverberated through much of biomedical research conducted by NIH, this notion that open data access is not just a good thing, it's almost a responsibility if you're doing something that other people could use. Obviously, the private sector model could not adopt that, or there would be no possible profit. And I think it's a very good thing when the dust all settled, the ultimate version of the human genome that everybody started using and now uses frequently, many times a minute, is publicly accessible without any restrictions. That was the right answer. And there are no more business plans, I think, of companies that aim to try to generate that kind of very fundamental pre-competitive data as some sort of a database that you would have to pay for. This just ought to be out there. And it is, which is great. So to be able to stand at the helm of that and to work with these 2,500 scientists in 20 laboratories in 6 countries, only about half of whom I had any real authority over because the rest were supported by other agencies. But it was still a wonderful experience. It certainly helped me learn a lot about team science, about how you can try to get the best out of every brain that's involved in order to make this project something that's better than any of us could have done alone. And that model, which was the first time really attempted for biology, and the fact that it succeeded has now spun off many others, whether it's 1,000 Genomes Project, or whether it's the microbiome, the Cancer Genome Project, or the ENCODE Project, which has just produced this amazing deluge of information about how the genome functions. Those, I think, all build upon the success of the Human Genome Project with the confidence that this is a model that works.
So, with regard to team science, what do you say to those who have inferred that, given your own personal experience and the decision that are made some by your predecessors at the helm of the NIH, that the NIH is funding more team science rather than more investigator initiated R01 type projects?
I don't think that's an NIH decision. And the shift is actually pretty modest. I think the trends reflect the way in which scientists have a desire to get things done. And if you're starting out today as an assistant professor in one of our top-notch universities, you might very well write an investigator-initiated R01 on a project that you are going to be able to make great progress on. You'll probably depend on a lot of these public databases to help you. But you might also say, you know, I want to do something that I can't do without bringing in this other individual with their disciplinary skills, or maybe 3 or 4 other individuals. It's not that we're forcing people to do team science. People want to do this because of the opportunity to go faster, to make breakthroughs that you couldn't do yourself. And we obviously are invested in progress. If you look at the distribution of how our grant funding is spread through the portfolio, many people are concerned that we've shifted more in the direction of translation and less in basic science. Those proportions haven't really changed, not in the last 10 years. I don't think they'll change much in the next 10. And some of the basic science is now team-oriented as well. It's not as if that's all individual R01s, although there are plenty of those there. So I don't think people should be anxious that there's somehow a top-down plot here, a conspiracy to force scientists into team efforts that they don't want to be part of. It's just often that's what scientists want to do, because that's how you can get a lot of work done. It's very gratifying. And I think those who've had that experience find that to be a wonderful alternative to the somewhat more lonely existence that was often the case in the past. A big challenge, of course, is to be sure that universities and other institutions that recognize excellence and make decisions about promotion and tenure value scientists' team contributions and don't just count, last author papers in Science, Nature, and Cell. And I think most universities are figuring this out, that if we are going to nurture the kinds of talented scientists in our midst that we really want to reward, that we can't just pretend that it's the same old situation it was 30 years ago. That team contributions need to be quantified so you knew what that person did. But if it turns out that's a critical part of a larger team, that matters a lot and that ought to be rewarded.
Right.
I guess there's a quote from Harry Truman that I'm fond of, which is amazing what you can get done if you don't care too much about who gets the credit. And that's certainly been true of many of these large team efforts. And I would also say, I talk a lot to investigators who've been part of these teams as sort of junior assistant professor level and say, did this hurt you? Did you get somehow lost in the shuffle because of a large project with many participants? Have you been injured? I've never heard anybody say yes. I've heard a lot of people say, oh my gosh, this has helped me hugely. I got all these connections. I got access to the kind of science I could never have done myself. I built collaborations on future projects. This was great.
All right. I want to bring you back to a question that I didn't ask you before. And that is that when you were working on the Human Genome Project, there must have been a tremendous number of ethical questions related to that work and what that information was going to be used for. How involved were you with GINA and passing a lot of the legislation protecting how that data was going to be used?
I was deeply engaged in the ethical, legal, and social issues related to genomics. And as you know, this was a new experiment where a government-sponsored scientific project decided to take responsibility for investigating those ethical, legal, and social issues before they became crises. So the ELSI program, ELSI, Ethical, Legal, and Social Implications, the Genome Project from the very beginning, started by Watson and then very much encouraged and expanded by me, was a critical part of this enterprise. And the goal really was to look forward and say, okay, suppose this project actually succeeds. What are the issues that we're going to want to think about in terms of making sure this has maximum benefit and minimum risks to society? And it was a long list of issues, but a very prominent one, and one that then got right in the midst of this mix between science and ethics and law and public policy and legislation, was the idea of genetic discrimination. That as individuals increasingly got more information about their genomes, that might be used against them, and particularly in terms of health insurance and the workplace. And so, fairly shortly after I arrived at NHGRI, we started a working group to look at that issue, ended up publishing a paper in Science making the case for a legislative solution at the federal level for both the case of health insurance and employment discrimination. And in 1996, the first bill got introduced to try to address this. We had a number of champions in the Congress who put a lot of effort into this, particularly Louise Slaughter and Judy Biggert in the House. It, despite all that, took an amazingly long time to finally achieve the outcome. But it was a great day indeed to be in the Oval Office as President George W. Bush signed the Genetic Information Non-Discrimination Act. I have a copy of that he signed personally to me on my wall. That was a wonderful partnership between scientists, the government, advocates, public policy experts, people who worried about civil rights, because in many ways this is a civil right. You don't get to choose your DNA. It shouldn't be used against you. And we won on that one. And that provided, I think, a great additional sense of confidence for people who wanted this information, that it wasn't immediately going to be used against them. It doesn't solve all the problems. It doesn't say anything about life insurance or long-term care or disability. There's still the potential there of discrimination. But the two biggest ones, health insurance and employment, you may not have that used against you, or you have a legal case to bring a grievance.
Now you speak about dealing with politicians and congresspeople and even presidents. What's effective as NIH director to work with these politicians to get them to understand the need and the importance of biomedical research? I imagine you must spend a disproportionate amount of time working on those issues as opposed to the scientific ones.
It's a big part of the NIH director's job, is to be immediately responsive to any request from the Congress for information. And we are always glad to get those requests. And over the course of the last year and a half, I have visited one-on-one with close to 200 members of Congress in the House and the Senate, answering their questions and trying to make the case for why medical research has arrived at such an important and exciting juncture in terms of its implication for advances in health and also why it's such a great investment in our own economy at this time where everybody is justifiably concerned about our fiscal situation. And I can tell you quite frankly that every single one of those conversations have gone well because our case is so strong. The evidence that we have to provide, to undergird what NIH has done to advance the cause of human health in the last few decades is overwhelming. And the evidence that that has also been a major source of economic growth for our country is also overwhelming. So the facts are on our side, and the opportunity to present that turns out to be generally quite valuable and gratifying. We also invite members of Congress to come out to NIH to walk around and talk to scientists working at the bench or go to the clinical center, our 240-bed research hospital, and see what's happening in terms of patients enrolled in clinical trials at the cutting edge of what's possible for cancer or HIV/AIDS or whatever the condition is that they're there for. And those invariably end up being an inspiring experience for everybody involved. I'm glad to say that many universities also take on this role, invite their elected representatives to come and visit. I wish they would all do it. I wish they would do it over and over again, because we are, as you know, at a very critical juncture right now. The support of biomedical research in the US has been under considerable stress. We had that wonderful doubling of the NIH budget between 1998 and 2003. It must have been a great time to be the NIH director then. But since then, the support for biomedical research has gone flat. And inflation has been eroding that. We now actually have about 20% less in terms of resources to put into medical research than we did 10 years ago. We've been undoubled. And that is extremely frustrating when you see the potential for breakthroughs that we are trying to pursue, but we could go so much faster. And it is particularly frustrating for investigators who are sending their best ideas to NIH and who in the old days at least had one chance in 3 of getting funded, which is now down to about one chance in 6. And for many investigators who spend an inordinate amount of their time writing, submitting, rewriting, resubmitting grants, trying to keep their labs going, this is a very tough time.
Right. When I told my PhD mentor that I was going to get a chance to talk to you, he wrote me in an email, "Tell Francis I said hello and to do something about the pay lines." So what do you say to people like Dr. Chris Waters at the University of Tennessee?
I would say he's exactly right that we need to do something about the pay line, but there is no magic where we can just twiddle a dial here and make that one chance in 6 go back to 1 in 3 without having the overall base of support begin to go back in the right direction. And that's not just a job for me, although I do everything I can to make that case. It's a job for all of us. The whole biomedical research community needs, I think, to recognize that we are not just an entitlement. We are actually a wonderful investment that the government makes, the public makes through the government, through NIH. But we can't expect that everybody just knows that.
Right.
And so all of us, especially now, especially with this deep concern about the sequesters looming over us, need to take some part of our time, and not in a way that misrepresents the facts, but simply explains to the public, to our elected representatives, why this is such an important thing for the US to be doing and what the damage would be if we allow this continued deterioration to go forward, where we might begin to lose important fractions of the newest generation of young scientists who just simply decide it isn't worth it to keep banging their head against this wall. This is a very serious circumstance. And no one out there who cares about this, I think, can assume that somebody else is going to send that message. We have to do this together.
Right. So in January, there's a real threat of sequestration. Would the NIH budget lose over 8%, correct? So how vulnerable do you think the NIH is to that enormous loss in funding?
If Congress takes no action between now, here we are in late September of 2012, and January 2nd, then these sequesters will kick in. It's not that somebody has to do something to make it happen.
Right.
It will happen unless action is taken. The Office of Management and Budget has issued an estimate of what that would mean, including an 8.2% cut in NIH support, which would be about $2.5 billion, disappearing on that day, already 3 months into the fiscal year. Since about 3/4 of our funds are tied up in multi-year grants, the average length of a grant we give is 4 years, what we can do in a single year where you have a sharp drop like that falls extremely heavily on the new applications. And this could be an extremely dark year for people coming in for the first time trying to get support, because while it might be an 8% cut in terms of the overall NIH budget, it would be more like a 30% cut in the new and competing grant pool. And that would drop success rates to historic lows that would be very hard, I think, to justify or sustain. So it's a matter of great concern. Now, I hear many people saying, well, don't worry, this is probably not going to happen, but it is still very much uncertain how the prevention of this will come to pass.
Right.
We have at the moment not a whole lot of expectation that steps will be taken until after the election, and that leaves a very short period of time for Congress to act.
Right. So you spend a significant portion of time not only with Congress people, but I've seen you on the Colbert Report at least twice. So it seems that you also have a significant role in lobbying the outside public, the lay public.
I don't lobby, remember, I'm a federal employee. I educate.
I imagine those must have been rather entertaining experiences.
Being on the Colbert Show is unlike anything else you can imagine during this lifetime. It is a white-knuckle experience because he will not tell you where he's going to go with the questions. It is completely free-form. So yeah, probably the highest adrenaline levels recorded in human biology must happen with those sitting at his table. I'm sure mine would have been right in that category too. But it is amazing because he loves medical research and he brings people on to try to teach his audience, who may otherwise not be paying a lot of attention to research, what's going on, and does it in a very accessible form. I don't know if it's widely understood that he has a reason for his connection to medical research. His father was, at one time, the associate director of the National Institute of Allergy and Infectious Diseases back in the 1960s. His father was a very distinguished physician scientist.
Wow, interesting. I didn't know that. So I've also, at some of these NIH retreats and the ASCI meetings, seen you come out with your guitar in hand and sing, so it seems like you definitely have a sense of humor about all of, about your life. So are you embracing social media in 2012? Do you tweet? Do you have a Facebook page?
I don't have a Facebook page, and I've been advised not to because it might get really messy, but I am a tweeter. And I suppose after this interview, I should send something out in the way of a description of what we just did so that people will ultimately think about going to look at it. Yeah, right. It's certainly a way that we get the word out. And as we've just been talking about, we in the scientific community can't just assume that the world knows and appreciates what we do. We have to take every advantage to explain that, to spread the word about what an exciting time this is, both in terms of trying to generate public support, in terms of educating the public about the issues they're going to have to decide about, and in terms of trying to inspire young people who are trying to figure out what career path to take, that this is a great moment to come and join us. We're going to answer questions in the next few decades that we almost didn't know how to ask. And we're going to understand how life works at a detailed level that's unimaginable in the past, and also how to apply that for a revolution in medicine that will change utterly the way that we prevent and treat disease. And to be part of that, wow, who wouldn't want to do that?
Well, I decided to crowdsource via Facebook a question to you.
Okay.
And so I asked my Facebook friends if anybody had a question they wanted me to ask you. So from a college friend of mine who's an MD and a clinician at the University of Arkansas in Little Rock, he says, workforce projections estimate an increase in patient volume as baby boomers age and are having a longer life expectancy. Mm-hmm. But physician shortages in several geographical areas and specialties are common and expected to worsen. Yet funding for training programs is cut, or at least not increasing so as to meet those projected needs. Essentially, there's more old people living longer with not enough physicians and with higher demands for clinical care and less grants. What do you say to young physicians and scientists struggling in academics?
Well, your friend is voicing one of many problems here in terms of the mismatch between the needs and the ability to meet those needs. NIH as a research organization doesn't play much of a role in terms of training programs for physicians who are going out in practice, but we certainly play a role in encouraging physicians to get involved in science and then supporting them as researchers. We've recently undertaken a rather thorough analysis of our whole biomedical research workforce. trying to understand what are the inputs and the outputs, because NIH supports, either directly or indirectly through grants, most of the trainees that are getting educated in the US about biomedical science, the PhDs, the MD PhDs, the MDs. And we have not had a really good handle on that very complicated landscape. A report just put forward to me this summer by a group led by Shirley Tillman, chairman of Princeton, president of Princeton, actually lays out a number of pretty interesting points and recommendations. And one is that we are probably not doing a service to our trainees to put all of our training programs in the context of preparing people to be tenure track investigators in top tier universities in a very competitive sense, because the mismatch is obvious in terms of the number of trainees and the number of such positions. And unfortunately, we tend to imply to our trainees that that's the goal they should all have, and we call other things alternative careers, which makes them sound second rate. We really need to do something about the way in which training programs expose graduate students and postdocs to multiple career pathways, so that they have a chance to figure out what's the right fit for them, instead of setting people up for a circumstance where, by our count, only 23% of our trainees actually end up in those tenure track positions. The rest of the individuals end up in very exciting roles in lots of different places, but we haven't done a very good job in helping them prepare for that, and we need to do a better job of that. With physician scientists, that group did not get as far in terms of assessing what the needs are in terms of both quality and quantity of training. That's the next iteration we're going to be looking at. All I can say to your friend is we take this with great seriousness. We don't have all the levers to pull, but we have some of them, and at least the ones we have to pull, we should be thinking carefully about how to prepare that next generation to be productive and satisfied and energetic about their future, because they are our future.
Right. What would you have done if you were not an MD and scientist?
I guess I was on this path to become an academic professor of chemistry. And had I not decided to expand my horizons in the second year of a PhD program in chemistry, I might very well have followed that tack, and I'm sure that would have also been scientifically exciting and interesting. But I'm really honored and delighted by the doors that have opened since then, that have greatly expanded the kind of science that I've had a chance to participate in my own laboratory, in efforts such as the Genome Project leading large teams, and now in this position of trying to steer the ship called the NIH in the direction that means the most for the public and for the scientific community. I could never have imagined that as this kid growing up on a dirt farm with no plumbing in the Shenandoah Valley. So anybody who's listening to this, particularly who's sort of in an early phase of their own career, if you feel like maybe you haven't quite got it straight yet in terms of what your path should be, don't worry. If you have it figured out, you're probably going to be wrong. So just be available to things that come along you didn't expect, doors that opened that you didn't know were there, maybe a door that you thought you were about to walk through that seems to be closing. Be flexible. Science offers you so many opportunities to do so many fascinating things, and nobody at this point should imagine that you can just plan a linear pathway for your career and have it turn out that way, because it won't. But that's okay. It means that we have a chance that maybe our predecessors and earlier generations didn't, to be able to have a scientific life that is truly broad, truly remarkable, truly rewarding, and the chance to work with lots of other interesting people and do things for humanity that are happening at a really dramatic pace. What a great time to be working in this field.
Okay, the last question also from Facebook. What's your nickname? Can we call you Frankie?
Please don't. I'm still Francis. I will admit that when I was a little kid, this is hard to say, my mom and dad called me not Frankie, but Francie, and I am so glad that that one disappeared by my strong insistence by about the age of 10, although I still encounter people who knew me as a very small child who slip up, and I have to give them quite a strong talking to about how that should never escape their lips. I'm just Francis.
All right. Well, thank you for joining us, Francis. We really appreciate you taking the time to talk to us today.
Thanks. It's great to be part of your program.